Yes.
Andrei, you're clear to go.
Okay, thanks. Okay, so I hope you can hear me. And thank you. Okay, so last talk we talked about projected methods in flat bands in which the interaction is projected onto a set of flat bands with different quantum numbers and with different topology or quantum geometry. We said that if the flat bands were trivial, then the projection would have just given a classical Hubbard model, exactly solvable. But since the flat bands that we're interested in have some quantum geometry or topology, or both, if you have topology, you got to have quantum geometry, but the other way is not true. Then these Hamiltonians, these projected Hamiltonians, are not exactly solvable, but sometimes you can get exact ground states based on the property that are positive semi-definite. We also said that remarkably, you can find their excitation spectrum, certainly the charge 1 neutral and charge 2 excitations, as a 0 and 1 body problem. And because the many body states were very easy, they were just ferromagnets in Slater determinants, and hence the excitation spectrum on top of them becomes easily solvable. The excitation spectrum has now bandwidth, and the bandwidth is given by a convolution of the interaction and the Fubini-Studi metric, or generalizations of the Fubini-Studi metric, hence giving a clear sign that quantum geometry is important for getting bandwidth out of flat bands. We also showed a theorem that you cannot get Cooper pairing for projected interaction. So Lattinger-Kohn does not work, even though the Hamiltonian is not solvable, and you have interesting quantum phenomena there. You cannot get superconductivity, you cannot get charge to bound states. And this basically led us to ask all these questions about the projected method. And moreover, the validity of the projected method is kind of put into question because the Hubbard-U interaction is stronger than the gap between the flat bands and the next set of bands, for example, in the Bissett-Samignono model. But we also said that really the most fundamental issue with just the projected method is that is not apparent, or doesn't solve what is a juxtaposition basically of different physics in the twisted bilayer system and in the twisted trilayer systems, really, which suggests that some properties can be understood as local moments, and these are STM and entropy properties, and some properties can be understood from delocalized electrons. And this kind of problem was early on noticed by Pablo Herrero in one of his abstracts, and this is a quote from one of his abstracts here. So if we're to take the physics at face value, we would think that really what's needed is a heavy Fermion model. Why? Because the localization or the local properties, the local moments, the sort of large charge density on the AA moire regions would be given by a localized heavy Fermion, and the delocalized nature of the physics, superconductivity, etc., Chern insulators would be given by a conduction electron. Now, turns out that, and this is the subject of today's talk, that you don't need to do this phenomenologically. You can actually do an exact mapping, which initially was numerical, but now we can do it analytically, between magic angle, or not even magic, but twisted bilayer graphing and a heavy Fermion model. Now, the heavy Fermion model works well around the magic angle and not so well away from the magic angle, and we understand this now why. but around the magic angle, it works very well in understanding all the properties of the correlated states. Now, of course, ongoing work is necessary for finding the properties of states where there is no gap, or for the superconductors. But in this work, I'll basically tell you how to build the heavy Fermion model, how to calculate all parameters in a first principle way, and how to explain these, at least these properties that I said are not understood in strong coupling, which become very easily understood with the heavy Fermion mapping. Moreover, I'll argue that this heavy Fermion mapping is not just restricted to twisted bilayer. For example, it allows you to understand the physics in twisted trilayer, for which many body solutions do not exist because it has a large Dirac fermion, as the single particle spectrum is not gapped anywhere. And also for some other made up models, for example, twisted curves and other models. So I think this mapping to heavy fermions, we're sort of trying to think how to put it on a more general ground. I think it's could be true when you have flat bands that are close to another set of what we call passive bands, but which are not that passive when the Coulomb interaction comes in, and when transfer of Berry curvature happens, as I'll show you. So now the construction of the model. So I want to review two of the slides that I showed in the twisted bilayer. So remember, we talked about the symmetries of the twisted bilayer model, and these are the symmetries, and there's a valley symmetry. And the representations per valley of the flat bands are these: gamma 1, gamma 2, K2, K3, M1 and 2. Gamma 1, gamma 2, and M1 and 2 are one-dimensional. K2, K3 is two-dimensional. This is the Dirac node in the Moiré-Briand zone. Now, these are just labels, but you can see their characters here. And the fundamental thing that we spoke about is that we now know that there's no way of writing these bands as a combination of atomic orbitals, and hence all the models that have been written, that's a combination of atomic orbitals, and hence they're topological. But it turns out, as I said yesterday, that actually at any bandwidth, twisted bilayer, at least the Bistritzer-McDonald model of twisted bilayer graphene, is topological. And its topology is equivalent to the presence of 4n+2 Dirac points in an energy, in any bands from energy E to minus E. So if you pick a set of particle hole symmetric bands in a single particle model, you're going to have really 4n+2, or at least 2 Dirac points in this set of bands. And this is anomalous. It's anomalous just like a single Dirac electron is anomalous and has to exist on the surface of a 3D topological insulator. However, this is anomalous, but it's anomalous in the bulk. This doesn't sit on the surface, okay? And the fact that it's anomalous in the bulk is because the Bistritzer-McDonald model is a continuum model. It wouldn't, if it was, so you cannot build a lattice model out of this. Of course, the way you make it not anomalous is you couple it to the other valley. But this coupling happens at 2 electron volts, which is the coupling of the valleys in the initial lattice of graphene. So for the energy scales that we're talking about between 0 and 60 or 0 and 50 milli-electron volts, it doesn't happen, and the model is anomalous. This forbids symmetric and short-range models with any number of finite bands. And for example, 10-band models that were written before, or 4-band models, etc., have to break some of the symmetries. Most of them break particle hole. Some of them, I wouldn't say break, but they represent time reversal as non-local. So you can, if you represent time reversal as non-local, then you can build short lattice models, but time reversal should be a local symmetry. So if you want to build models with local time reversal, etc., with all the symmetries, short range, you cannot do it. Hence, the question is, where do these states that are observed in STM that act like they would be very localized, where do these states come from? Since we know you cannot write these bands as localized orbitals, how do we build them? Well, the first hint on how to build them is to look at the fact that the problem with writing the Bistritzer-McDonald bands, or these two bands here, as localized orbitals actually lies at the gamma point. They have the wrong representations for localized orbitals at the gamma point. You know? So at the gamma point, it turns out if you were to replace the gamma 1, gamma 2 representations of the bands with actually a gamma 3 representation, as you see here, then you would immediately see that a gamma 3 representation at gamma point, a K2, K3 representation at K point, and an M1, M2 representation at the M point, if you look at the Bilbao crystallographic server, are equivalent to localized orbitals at the 1A Wyckoff position. So exactly where the AA stacking, where the STM images sees the largest charge, at the AA Wyckoff position, they're equivalent to PX and PY orbitals at the Wyckoff position, at this Wyckoff position. So now, how do we get the gamma 3 representation? Well, we immediately see that there are bands which are close to the flat bands, which have gamma 3 representation. These are just the next bands in the Bistritzer-McDonald model, which actually sit within Coulomb energy scale range of the flat bands. Hence, we're going to take, for example, a window of plus minus 60, plus minus 70 electron volts, and consider all the representations in this window and borrow one of the gamma 3 representations and try to build Wannier states from this. So we introduce Gaussian type wave functions, which are px plus IPY and px minus IPY. These are the actual representations of the two. They're related by C to T. They form a two-dimensional representation at the gamma point, gamma 3. And we introduce these Gaussian wave functions, and we project them onto the Bistritzer-McDonald bands. We introduce them into the Wannier 90 Wannierization program, which builds you maximally localized wave functions, and the output is a set of maximally localized wave functions. Questions? Which? Yeah, please go ahead.
So you said that this is more than a. You said that this is more than a fragile topology. But aren't you just treating the problem as having a fragile topology by turning it into a heavy fermion problem?
So the problem will still have strong topology, because the conduction electron, which will be quadratic, has topology at any bandwidth, right? So at any bandwidth, you'll see in the quadratic fermion, which will come in the next slide, or in 2 slides from now, it will have the topology will still, the strong topology will still be there, because this double vortex you cannot get rid of. So we're fully taking into account the presence of stable, strong topology. Does that make sense? So in fragile,
thank you.
In fragile topology, yes. So very good. So in fragile topology, if you add some other bands, you would be able to trivialize these bands. But no matter how many bands, if I just have the same symmetries and add to a quadratic fermion, this vortex, this double vortex, I cannot get rid of. So there's going to be the bands might hybridize, etc. But the double vortex I will not be able to get rid of with these symmetries. So the topology, the strong topology is the model is faithful to the strong topology in the end. It's a very good point. So we're just basically putting the topology where it should be, which is this double vortex, which is the 4n+2, the 2 of the 4n+2 Dirac fermions. So the 2 Dirac fermions become a double vortex. They carry the strong topology. Very good. Yeah. So this is very important. We're not making the model fragile. It's still strong.
So you've accomplished that by using continuum conduction electrons.
Exactly. But the initial model is also a continuum model. So the Bistritzer-McDonald model. So it's not I'm not introducing anything that's not originally in that model. The initial model is also a continuum model, the Bistritzer-McDonald, and I'm just representing it differently in a way that the topology becomes evident, if that makes sense.
Thank you.
Thank you. Okay, so we introduce these Vanier states. We get out of Vanier 90 the maximally localized Vanier functions. It turns out, of course, they're localized at 1A, but their localization spread is 0.2 the Moire lattice, so they're very localized, which gives rise to a hopping between them of 0.1 electron volts, which we're going to say is 0. So this is an incredibly small hopping. So the Hamiltonians of these guys is really 0. They're really flat bands at 0 energy. And then you can compute their overlap on the bis system, on the flat bis system McDonald bands, this on these 2 bands here. You can compute the overlap of Vanier states. You know it cannot be 100% because the representation of the Vanier states at the gamma point is gamma 3, but the representation of the bis system McDonald bands are gamma 1, gamma 2. So they're orthogonal, but you can ask how much are they? And it turns out they're 96.6%. So 96.6% of the bis system McDonald bands are expressible of the flat bands are expressible as these localized Vanier states. So where are the remaining 4% of 3.4% the bands? These are the guys that are sitting here. What Piers was mentioning in the previous slide. Basically, what we're talking about, they're the guys that are sitting here. And how do we get them? Well, what we know is that in order to build these Vanier states, we actually looked at the bands within plus minus 50 electron volts, 60 electron volts, so that we have these gamma 3 representations, which are the next ones. Within this energy range at the gamma point, we have 2 gamma 3 representations, right? 2 gamma 3 plus a gamma 1 plus a gamma 2. But we've already used the gamma 3 representation to build the Vanier states. So what's left over is a gamma 3 plus gamma 1 plus gamma 2 representation. We build the projector into this representation because we know the projector into the heavy fermions, which we're going to call from now on F electrons by abuse of language. The representation is px, py orbitals at the 1A lattice, Moire lattice site, at the triangular lattice site. We build the projector into these fermions. We take 1 minus itself. This projector contains exactly the representations gamma 3 plus gamma 1 plus gamma 2. And you can build a Hamiltonian for them by taking the bis system McDonald Hamiltonian into the eigenstates of this projector, dotted into the eigenstates of this projector. By symmetry, you can also build it. It's going to have, for example, 0 in the gamma 3 block, because the gamma 3 block is a 2-dimensional representation. It's going to have an M, which sigma x, or a splitting in the gamma 1 plus gamma 2 block, because the gamma 1 and gamma 2 representations are 1-dimensional, they can be split. And since this is an angular momentum 1 representation, and this is an angular momentum 0 representation under C3, they're going to have a linear term between them. And these velocities, V star and M, these velocities are basically obtained numerically, but I can show you afterwards that we are now able to obtain them analytically. But you can obtain them numerically from the bis system McDonald model, and these are their values. In particular, this M is very small. And you can see what this M is. This is the difference between the gamma 1 and gamma 2 representation energy. So actually, it represents the bandwidth of the bis system McDonald model in the end, right? The difference between the gamma 1 and gamma 2 representation is just this small here bandwidth of the bis system McDonald model right here, okay? The difference between gamma 1 and gamma 2. And now you can understand what this Hamiltonian is. This Hamiltonian is a gamma 3 representation at 0, this guy, a 2-fold representation at 0, and a gamma 1, gamma 2 representation, which are split by M. But if you look at it, this is exactly the Hamiltonian that you would get at, for example, one of the points of the untwisted AB bilayer graphene. So untwisted AB bilayer is exactly this Hamiltonian, and it has a quadratic touching. This quadratic touching is the 2 Dirac electrons put together, and it's a quadratic touching, and it's carries the topology. And as Piers mentioned, the fact that it's strong is basically because it goes all the way to infinity, and you basically don't have a bandwidth. There's no way to write this with a bandwidth, because we know the bis system McDonald model is topological at any bandwidth. And hence we now have both the heavy electrons, which are very localized. Hamiltonian zero sit at the A site. And then we have an AB stacked, untwisted, stacked a conduction fermion made up of 4 states with a double Dirac vortex here that carries the topology, and that comes from AB, the AB regions basically. And now the physics is more or less done, with the exception that we have to couple the 2 parts. We have to couple the heavy and light electrons. So the heavy electrons sit here, they're these localized. The light electrons basically come from the AB region, and they are here. Okay, so this is somehow a mistake, this elongated figure. And their coupling is, again, actually easy to write down. And it comes like this. It actually turns out that to first order, the coupling is just a constant, and is the coupling between the gamma 3 representation of the F electron and the gamma 3 representation of this this is a double representation, the gamma 3 representation at the gamma point of the C electron. And this is this gamma. Then you actually, to represent fully the system, you need a linear order term, which can be obtained by symmetry. Their values can again be obtained from the Bicester-McDonald model, but now we can obtain them analytically. And this gamma is actually a large value, it turns out. It's not going to be the largest energy scale in the system, but it's a large value. It's around 20 milli-electron volts. It varies actually very strongly with W0 over W1 with the AA interlayer hopping and versus AB interlayer hopping ratio. So now we have the entire model, and this model is for energetic purposes. If you don't want to take into account everything, you can sort of consider a 6x6 model, but it actually has umklapp if you want to get the correct degeneracies at the K point of the fermions. You know, if you consider just this model, you're going to have a small splitting at the K point of the heavy fermions. If you take the next Brion zones, you're going to get the correct velocity of the Dirac fermion here, and degeneracy. But this model, if you want to consider just the energetics, it's a 6x6 model. It's 0 in the heavy fermion Hamiltonian. In the gamma 3 C fermion is this is the block, and this is the gamma 1, gamma 2 block of this conduction fermion. And you can see the conduction electron, which is this AB unstacked double vortex plus 2 states here. Okay, and now couple it. You can couple it through the gamma plus another linear term with the through this gamma to the conduction electron. You can couple the heavy fermion to the conduction electron, and this coupling being large is the coupling that gives you actually the gap between the Bicester-McDonald flat bands or flattish bands, these 2 bands, and the next set of bands. So in this model, M being the gamma 1, gamma 2 energy difference is the bandwidth of the Bicester-McDonald model. Okay. And gamma is the gap between the Bicester-McDonald flat bands and the next set of bands. And these are the 2 energy scales that you need to look at, and these velocities are also obtained from first principle. Now the hybridization, this gamma hybridization, is larger than the bandwidth, but as we'll show below, smaller than the on-site repulsion. So any questions up to now? Okay, so if there's no questions, we can.
There's a question coming.
Okay. I cannot hear you.
try that.
So, hi, Andre.
Hi.
And I just wanted to ask a physical kind of understanding between the coupling between the conduction ABs and the Fs at AA. The form of the hybridization, do you have a physical, apart from kind of getting the Bistritz-McDonald band structure, do you have a kind of intuition about, you know, why the form of the hybridization is like this?
Oh yeah, so I mean, nothing here is guessed, okay, right? So as you know, like everything is computed, and the hybridization has to be like this by symmetry. Okay. In fact, there's another, you know, this doesn't have to be zero by this. The hybridization between the F and the C electrons, the gamma has to exist by symmetry because it's two gamma 3 representations coupled. So they will have, if I take gamma 3 times gamma 3, I'll get a identity representation in the decomposition. So it's got to have a gamma, it's got to have a constant. Then a linear representation, a linear term also can exist by symmetry, and you can prove by symmetry. And the zero is not actually zero. A small linear term has to exist, but we find that can exist, a small linear term can exist because this is a coupling between a gamma 3 representation and a gamma 1, gamma 2, which is angular momentum 1, and this is angular momentum 0 under C3. So there can exist a linear term here. There just cannot exist in the smallest. There just cannot exist a constant term. But we find by numerically that this linear term here is very, very small. Okay, it's about 2 orders of magnitude even smaller than this term. So that's why we put 0. But this form is fully given by symmetry. The only thing that you don't know by symmetry is the values of these constants, which you can compute by looking at the Bistritz-McDonald Hamiltonian. So if I didn't know about the Bistritz-McDonald Hamiltonian and I wanted to compute this term, and I wanted to compute this coupling, I could get the value. I could get the form of the coupling. I would get that here. There's another linear term, which then, if I would compute by symmetry, if I would compute its value by you know, dotting these eigenstates into the Bistritz-McDonald model, I would find this very small. Very good. Thanks for the question. So none of this is guessed, right? So everything is, and this is a form by symmetry. Now, of course, what the symmetry does not give you is the values of these constants. For example, even by symmetry, you could have a heavy fermion Hamiltonian, which is not 0, but because these are so localized, the hopping between them is 0.1 me-electron volt, so we put this to be 0. Very good. So then with these parameters, you can ask how well does this do at fitting the Bistritz-McDonald Hamiltonian, and this is how well it does. The black lines are the heavy Fermion model, and the red lines are the Bistritz-McDonald model. And actually, this good fitting remains for not only for the magic angle, but for a large range of parameters around the magic angle. I'll show you what changes for the large range of parameters, and when the heavy Fermion description doesn't become that is not good anymore. I'll show that to you soon. Okay, so now, given that the non-interacting physics is solved, there's no advantage to this formalism other than, you know, what I think is beauty, but that's in the eye of the beholder. So you know, other people might find it atrocious, but there's no advantage to this formalism unless these degrees of freedom that we separated into mean something. And for that, we compute the interaction, and you compute the interaction Hamiltonian. And it turns out that the most important terms are the following. As we sort of expected, the largest term in the problem, this U1 term, is the Hubbard U between the F and F electrons. And this is a huge energy scale in this problem, about 16 electron volts. So it's the largest energy scale in the problem. So now you've got a starting point where you've identified the largest energy scale in the problem as being the Hubbard U of the F electrons. And these are really heavy fermions localized with large Hubbard U. Then the next thing is density-density interaction between the C and F electrons, and this will act in the end as a chemical potential for the C electrons at different filling, and the filling will be given by the F electrons. So the F electrons will govern the filling in the end, and then they'll act as with a chemical potential for the C electrons. And importantly, the term that would actually break the degeneracy of the double vortex in the C electron when you go to the correlated insulating states is a coupling, which is a coupling between the F and C electrons, which so far I haven't written down nicely, but I will write it down nicely as a ferromagnetic coupling between U4 moments of the F electrons and the C electrons. So now we see that U1 has to be the main source of symmetry breaking if there is symmetry breaking, and we'll see the cases in which there is and in which there isn't. And the hybridization is much smaller than the symmetry breaking, even though it's still a large energy scale in the problem. And then I want you to remember there's this J term, which is a ferromagnetic coupling between some moments of the F electron, some moments of the C electron. So now I'm going to make a quick intermezzo and show you that actually, basically, this is ongoing work, all of these parameters that I showed you before, like U, etc., M, prime, etc., can be obtained analytically. So it turns out that you can obtain all these parameters within actually 30% error of the numerical expressions over a large range of angle analytically from the Bicester-McDonald Hamiltons. It's W0 Bicester-McDonald. These, then you plug this in here and you can obtain V prime, etc. So you can obtain all these parameters of the heavy fermion as analytically from the Bicester-McDonald model, doing some careful identification at different points of the models. And now I wanted to show you the numerical, so numerical and match within 30% by analytics values of the parameters of this heavy fermion model within a larger angle range. So here the horizontal axis is the angle, and the vertical axis is the ratio of W0 over W1, or AA hopping over AB interlayer hopping, AA interlayer hopping. And I remind you that this value in graphene is around 0.8. And the chiral limit that people talk about is 0. Okay, so for example, these are the localization of the Vanya states. Okay, and you can see that the localization of the Vanya states, basically, doesn't vary very much. I mean, they're still they become less localized as you go towards the chiral limit. This is not 0, it's numerical error. They become less localized as you go towards the chiral limit, but not by much. The important things that I wanted you to look at are the M parameter, i.e. the bandwidth of the Bicester-McDonald model, but given a bandwidth at the gamma point between gamma 1 and gamma 2 representation. And here you see a clear decline at the magic angle. So this is the magic angle. Okay, this is this red, zero, this white thing, the 0 is exactly the magic angle. It's got very little bandwidth, and this is just telling you that the Bicester-McDonald model at the magic angle has very, very small bandwidth. This you knew. This thing here, okay, is the hopping between the Vanya states as a function of the angle. So the F localized, the F electron Vanya states which hop, and you again see that at the magic angle, very close to where this guy is, there's 0 hopping or all very small hopping between the Vanya states. This is not the same as the bandwidth being small. This is the fact that these actually coincide is kind of surprising, because the hopping between the Vanya states influences, for example, the bandwidth around the K point and the M point, whereas this M parameter, which is the difference between the gamma 1 gamma 2 representation, is the bandwidth at the gamma point. So the fact that they're zero in the same, or close to zero, very small, in the same range around the magic angle is surprising to me, at least. And the next thing is, the next thing to look at is the percentage of the Bicester-McDonald bands that are made up by these f orbitals. And you see that, towards the chiral limit, it's a far less percentage, but it's still about 80% of them, even in the chiral limit. Of course, it's very large around the physical, the realistic flat bands region. It's larger than 97, 96, 97%. If you tune the angle around the magic angle, etc., around here. But it's large everywhere, even in the chiral limit, which is very far away from the reality. It's about 80%, which basically tells you that the heavy fermions have the correct representations at the K point, at the M point, and of the Bicester-McDonald bands. Hence, they're going to have some overlap everywhere. The next thing that I wanted to tell you is the FC fermion coupling. And this is the FC fermion gamma. And you can see that this heavy fermion to conduction fermion coupling gets very large in the chiral limit, minus 180 milli-electron volts, so incredibly large. And this is the key to the validity of the heavy fermion model. These are how the U parameters vary with the, this is on-site, this is nearest neighbor neglected, U2 is nearest neighbor, it's much smaller, you can see, but this is the on-site U of the F electrons and how it varies with angle. And you can see that in the chiral limit, or at these small values, it actually decreases and is large around these values. So I claim that the heavy fermion description is a good description for when this parameter, which is, I think this is well known, obviously, in the heavy fermion literature. It's just kind of new to me because I'm not versed in it. But this parameter, which is the coupling between the F and C electrons over the F electron Hubbard U, is small. And this coupling, you can see that it's small only over a small region, or not small region, but not a large region around here, including the magic angle, which is somewhere around here, and including the 0.8 with W0 over W1, which is the correct value of the realistic parameters. So you can see that in the, for example, the chiral limit, or at large angle, for example, you can represent the Bicester-McDonald model as a heavy fermion coupled to this conduction fermion. And I think this is a, this is the correct and valid description. The point is it useful? And I think the answer is no at these other angles, because gamma, i.e. the coupling between the F and C electrons, is much larger than the Hubbard U. You see this 3 times larger in this area, etc., than the Hubbard U. And this also might be the reason why there's no correlated states in that region. If the coupling between the F electrons and the conduction electrons is much larger than the Hubbard U, then there's no energy, or there's no obvious energy to be gained by ordering the F electrons. So with that, I want to show you how you can get the correlated states. And if there's some questions here, I can take some questions on these plots and why the heavy fermion model should be a very good approximation and a very good way to understand the physics.
Questions coming.
Yeah.
Andrei, I have a question about this ferromagnetic coupling that you got, I think, from just Coulomb integrals, as compared to what you would get from a super exchange. So do I understand right that the ferromagnetic always wins?
Yeah, so I don't know. Actually, Pierce and his student Lim are doing that calculation now. So I don't know if So if you would integrate, so what you're saying is if you would integrate out the C electrons, right, as you do in the Schrieffer-Wolff, and you'd get some other J, which one would win? And the answer is I don't know.
Okay, thank you.
That's a very good question. We didn't calculate that. So this is just coming from the this is just the interaction coming from the projected density into the spaces. But we didn't integrate out the FC. We didn't remove by Schrieffer-Wolff the FC coupling and to get a new J and to find which one wins. And I would assume it wins in some. I would assume the new J, if I was to speculate, which I cannot, but maybe Liam and Piers can say more. I would assume it wins in some situation and not in others, because in some situations there's, yeah, actually, let me not speculate. I don't know. The answer is I don't know.
Okay, thank you.
Thank you.
Thanks.
Thanks. Okay, so so coming back to this J, actually, in order to write it down more nicely, it's interesting to look at the symmetries of the problem. So the previous study here, by previous study, I mean the strong coupling expansion, just projecting into the heavy bands. Let me just get a mint. Projecting into the Biston-McDonald flat bands. The projected Hamiltonian was shown to have different kinds of symmetries in different limits. If I would just project, it would have a flat symmetry, flat U4 symmetry, because the particle hole, so this was alluded to in last talk, particle hole times C2Z will give you a flat U4 symmetry for the projected model. It would be broken by the kinetic energy. Then in the chiral limit, which is this W0 equals to 0, you'd have another U4 symmetry, which is given by the chiral. So in the end, you'd have a U4 times U4 symmetry of the flat model. Now, in this Hamiltonian, the U4 symmetries also exist, but they commute with the entire Hamiltonian, not just with the flat Hamiltonian. Okay, so for example, the flat limit, i.e., the limit in which these bands are exactly flat, okay, that's the M equals 0 limit. I remind you that M was of order 3.4 electron volts or 3.74, something like this, and twice that was the Biston-McDonald bandwidth. And and if I put this to 0, I have an exact flat band, and then I have my entire interacting and kinetic Hamiltonian commuting with U4. Then we can also go, but now this is going to be the end of me talking about the chiral limit, because it's not a real limit that the physics is in for this model. You can also have a chiral limit of this model, of this Fermion model, and the chiral limit corresponds to V prime equals 0, where there's another symmetry, there's another chiral symmetry which can give you another chiral E4. So basically you can get all the symmetries that you would have gotten in the projected model, except this model is not projected now. These are the generators of these symmetries. Okay, so we can show them in explicitly, and with these generators, you can rewrite this J term as a U4 fundamental of the F fermions times the U4 fundamental of the C fermion. So it's a ferromagnetic coupling between the representations of the F and C fermions. And this is the Hamiltonian that we'll now use to obtain the many-body states. So again, as I said, in the projected study, the many-body states were Slater determinants, basically ferromagnets, of these projected Hamiltonian, which you could prove by positive semi-definiteness in some ranges. And then you had these large U4 symmetries by which you could rotate around the manifolds. Okay, so for example, I'll explain what a KVC state is in a little bit, but there were, you know, at filling -3, you can just occupy one band and it would be a ferromagnet with a Chern number. Actually, it turns out that this is unstable, even in this formalism. But at filling 2, you would get a stable, plus or minus 2, you'd get a stable ground state, which would actually be Chern number 0, but would have linear combinations of these of what's called the valley, what's called coherent intervalley state. And we'll get to this in a little bit. Now, again, as I said, the excitations above these states, even though you started off with a flat band in the projected limit, actually had dispersion. And this was because of quantum geometry. We explained the flat bands, but we didn't really understand why the dispersion at gamma point, etc., etc. So now, I want to show you how you can get this and the understanding of all these properties from the heavy fermion problem. Now, how do you build ground states at a given filling? Well, I'll give you an example for filling 0, and of course you do the same for every filling. What governs, you build the trial state, which is the parent state, and what governs the filling is the F fermions, because of the Hubbard U, the most you can gain is by filling the heavy fermions, and that's what governs the filling. So for example, at mu equals 0, I fill 4 of my 8 heavy fermions. So I have 2 heavy fermions per valley per spin. So 8 in total. So I fill 4 of them. And then I also fill the Fermi C of the double Dirac vortex. Now, the way I fill these heavy fermions is by a U4 Hand rule to form this U4 representation. Okay? And when this parameter m equals to 0, so you can notice that, and then I can apply when this parameter is m equals to 0, the bandwidth of the Distel-McDonald model is 0. I can apply a U4 transformation on these because I have the U4. So any U4 transformation is a ground state, is a parent state. This is the parent state first. For example, this one you can clearly see is valley polarized. This is valley. The plus is a valley. This is the valley polarized state. The KVC or Kramer valley coherent state is applying this operator where these is one of the U4 generators, and it corresponds to this state, a linear combination of the heavy fermions, the 1 and 2 heavy fermions, the px py heavy fermions, px plus ipy and px minus ipy, in valley plus and minus. This is the valley coherent, valley plus and minus, you combine them. And in this state, you have that the initial time reversal symmetry is broken, but you have another time reversal symmetry, which is basically in Kramer's time reversal symmetry, which is a combination of one of the U4 generators of the F fermions times the new time reversal. And for these parent states, you can see that the expectation value of the F C parameter, F dagger C parameter, is 0, but the expectation value of the F dagger F parameter is non-zero, and it will govern the physics. So when m is equal to 0, these states are degenerate, okay? But when m is different from 0, these states will not be degenerate, and you have to find out which is the lowest state. And the way we do this is by doing actually Hartree-Fock on this parent state. So you take this parent state and you do Hartree-Fock, and what we find is that when the correlated insulator is stable, one-shot Hartree-Fock is enough. And this is crucial because then you can get analytical results. So on the left side, this is for the valley polarized state. We start with one-shot Hartree-Fock here on the parent state before. And you can see that the self-consistent Hartree-Fock, which is the second figure, is basically very similar to the one-shot Hartree-Focks. So we're just going to focus for the one-shot Hartree-Fock. This is for the valley polarized state. This is for the KVC state. And you can see here what we obtain, right? Looks very similar to what we obtained here, very similar to the quasi-particle dispersion that I showed you in strong coupling. But now we have a very easy way of understanding it. So what happened is you started off with this double Dirac fermion. And which is this guy here. And then at filling 0, you're going to split the F fermions to occupy 4 of them. So this has gone to U1 over 2. And this has gone to minus U1 2 or minus U1 over 2 and U1 over 2. Okay, or U1 and minus U1 depend on. Okay, so these have gone up and down. And now the gamma term or the coupling between the F and C electrons hybridizes this. So what you're getting in the end is going to be the following phase diagram, the following dispersion. And you can immediately see that this dispersion, the J term will open a gap here, okay? And this dispersion now looks exactly like the dispersion that I showed you in the excitations on top of the insulating state. So now you understand several things. What did we understand before? We didn't understand why the gap was the smallest at the gamma point. Now we understand the gap is the smallest at the gamma point because of the double vortex which exists at the gamma point, which is split. Everything else, the heavy fermions move up and down. The heavy fermions are the ones at the gamma point, okay, here, at the K point here and the M point at the edge of the Brillouin zone. The physics at the gamma point is governed fully by the double vortex, which is now split by the J term. The other thing that we didn't understand is the flatness of the zone boundary particle charge 1 dispersion. Now it's very easily understood. This comes out of the flat heavy fermions, which have moved up and down, and this is why this is flat. We didn't understand why the dispersion is so large. Well, this is clear now because the heavy fermions have a U. This gap opening here is of order J, okay, and the dispersion is U minus J, but J is about a quarter of the U calculated, and hence the dispersion is the largest here. So now all these things that we didn't understand from the projected Hamiltonian come here and come into this situation easily. Moreover, the other thing that I didn't write here, but it was clear in the projected situation. This was the charge 2 dispersion, and remember the charge 2 dispersion has some anti-bonding states, or basically meaning anti-bound states, which basically meant some resonance state above the 2-particle continuum, and that they were quite flat. These are clearly just filling in 2 F electrons, and they're at energy 2U. You just fill them up twice, and the energy matches, and they should be flat. This is just the filling of the Hubbard model, and they're much higher than the particle continuum. So all these properties of the projected dispersion can now be easily understood, or projected dispersion cannot be easily understood. But moreover, you can easily understand why the KVC state wins in this case, at least for homogeneous samples. For non-homogeneous samples, Yves Kwan and Sid Parameswaran have some C3 theory breaking where you can get other states, but for homogeneous samples, the KVC state always wins when you have kinetic energy. The reason for that is simple. Now, with this one-shot heavy fermion, as I said, we can do things analytically. So the physics is governed by the gamma point gap opening, and you just want to see which gap is larger. And with the density metric of the F fermions, which you can compute for KVC and valley polarized states, okay, just from the parent state, right? The parent state, which is the decoupled Slater determinant state, you can compute this, and it turns out that the Hamiltonian at the gamma point is almost zero everywhere, with the exception of this gamma. This is the U of the F electrons, and this is the mass of the gamma 1, gamma 2 representation. This is the J coupling of the F electrons with the C electrons which enter here. So now the question is, does this term commute or anti-commute with the J term? Does the M commute, anti-commute with the J term? If it commutes, which happens in the valley polarized state, you can see that they commute, then you get a gap which is J over 2 plus minus M. Okay. If it anti-commutes, which happens in the KVC state because of the structure of the F order parameter, then the gap becomes square root of m squared plus j plus minus, and the gap is larger. So then the KABC wins when m is non-equal to 0. When m is equal to 0, they're both the same because of U4 rotation. So these type of situations, you can apply them to all fillings and obtain all the correlated insulator states. I want to point out that at filling -3 and +3, both the projected method and the heavy fermion method, and I expect the heavy fermion method to be more accurate. Sorry, there's a chat. Let's see. Okay, so there's where does this? Okay, so the question in the chat was, where does dispersion arise from the heavy fermion picture? The dispersion of the charge 1 excitation arises from the fact that the double vortex has dispersion. It's basically the dispersion of the double vortex. You split the double vortex by J, but the heavy fermion moves way up. And then when you hybridize the heavy fermion with a J, the dispersion is basically all the dispersion of the C fermion. It basically comes because the C fermion is basically the dispersion between the small gap given by J, the J term of the C fermion, and the flat band of the heavy fermion, which now has moved at high energy because of the correlation.
Thank you.
Thank you. This is very good. So yeah, thank you. And now basically you can get this set of rules, which are very simple for ground states. For ground states, and I don't mean, so I mean correlated insulator ground state at integer filling. However, I want to point out that at filling -3 and +3, the Hartree-Fock spectrum that you obtain from both the heavy fermion and the charge 1 spectrum that you obtain in the strong coupling problem actually give you an instability. So at +3 and -3, these do not give correlated insulating states, none of these theories, and this is consistent with experiments. The nature of the state there in the MRG and other studies has been proposed to be either a charge density wave, but that's not entirely clear. The MRG studies and exact ionization studies, the latter of which we've done, are not very well. At least let me not talk about the DMRG. Let me talk about the ED studies. The sizes are too small because this is a huge Hilbert space, so you cannot really get the nature of the state there. So that's still under debate model-wise. Okay, so then I was also showing you that, for example, that at filling at filling 0, the quasi-particle excitations look like this on top of the insulating state. At filling -1, they actually, I was showing you, one of them was very dispersive. If you remember, I said that one of them was very non-dispersive, very different from filling. This is filling -1. It's filling 0. So what happens actually is very easy to understand. As you go from one filling to another, remember there was a rho C, rho F energy with a W in front of it. So the F acts as a chemical potential to the C fermions. And because of this energy, it just shifts up and down the C fermions. And at filling -1, it shifts them so that the F electron comes and sits basically exactly where the double vortex is. And hence, when you now introduce FC coupling, so this gamma term, when I introduce it, there's not much hybridization you get here. And hence, you can get an exact flat band, or not exact flat band, but almost a flat band, even in the dispersion spectrum on top of the correlated state in one direction. So this is for electrons, and this is for adding holes. Although for the holes, it's very dispersive, etc. So all these properties, you can understand them immediately. The Chern number of the states that you're getting, it can also be understood axiomatically because all you're doing is gapping a double vortex. And if you gap a double vortex, depending on the way you gap it in different values, different spins, you're going to get a Chern number or not. and the Chern number, the expression for the Chern number can be obtained analytically, depending on the states. This is the occupation number of the F fermion. And now I wanted to get to actually twisted trilayer, which is something that has escaped projected analysis, for example. And there's only 2 Hartree-Fock papers, one of which is ours, and I can safely claim that we don't understand a lot of the physics there. We understand some of it, but a lot of it we don't, because it's very hard to do Hartree-Fock on this system. So twisted trilayer graphene is a system where you now have, which has been realized experimentally, where you have 2 layers at these different angles from a 3rd middle layer, and they're in a mirror symmetric configuration, and they've been realized experimentally. And then you can apply an electric field to the system while gating it. So we'll call this displacement field. So at 0 displacement field, there's now a symmetric and anti-symmetric combination of the upper and lower layer under mirror. Okay, the symmetric combination forms a moire pattern with the middle layer. Okay, and it's actually exactly the same as TBG, twisted bilayer graphene, just at a rescaled angle, square root of 2 times the angle of TBG. So it's at a larger angle. So you should get exactly the same dispersion as the Bicester-McDonald model at this angle. And this is given here. It's exactly the same dispersion as the Bicester-McDonald model. Now, the anti-symmetric combination of the upper and lower layer, you see the upper and lower layer are not twisted. So the anti-symmetric combination just gives you graphene. And because of the valley symmetry, in the Moire-Briand zone, you have this extra Dirac fermion of large velocity. Actually, these 2 velocities are about the same. Okay, this velocity, I just drew it wrongly. These velocities are about the same. You have a Dirac fermion piercing the entire spectrum. So now you don't have any way to project, because the Dirac fermion prevents you from projection. So this is in single particle. In single particle, they don't talk to each other. In many body, they start talking to each other through density terms, because density terms have the same eigenvalues on the mirror. So they can talk in single particle, they have different eigenvalues on the mirror at 0 displacement field. As you add displacement field, something happens. So you can see that as I add displacement field, you can do the Bicester-McDonald model for this, and you get that this Dirac fermion is actually pulled away here. Okay, you pull it away by electric field, and you can see that since electric field doesn't break C2Z times time reversal symmetry, the spectrum is connected everywhere in the Briand zone. You don't have any gap anywhere. And the phase diagram of this guy with electric field is horrendously hard to calculate analytically. The symmetry is reduced with the electric field to U2 times U2. There's no more U4 symmetry, etc. However, in the heavy fermion description, the situation is very similar. And in fact, you don't need to do much work. You can just, basically get the heavy fermion from TBG. The only thing that you need to do is figure out the coupling of the heavy fermion to the new Dirac electron that appears, to this anti-symmetric combination of the upper and lower layer. And here I show you the matching between the Bicester-McDonald model and the heavy fermion in red and blue of the twisted trilayer. And you can see that even at large displacement field, this is a large displacement field, the matching is kind of superb. So you see blue and red, they're nice. So with Hartree-Fock, the mini-body also becomes very easy now, at least in some, I can't guarantee that they're all going to be ground states, just like in TBG at mu equals -3, your correlated insulator that you obtain here, that you obtain from the parent state of filling F electrons is not the ground state. There might be other ways of doing it of obtaining the ground state with heavy fermions in them. But just this way of doing it doesn't give you the ground state. But what I wanted to show you is that with the heavy fermions, the physics is the same. The heavy fermions polarize, and now the only thing that enters is figuring out the heavy fermion to the Dirac electron, to the highly dispersive Dirac electron coupling, and splitting that guy also. And you can see that at mu equals 0 in moderate displacement field, actually, you still get the KAVC state as the ground state. At mu equals to -1, you get a metal. You can see that the state is metallic now. And at mu equals -2, there's still metallic, the state. And this is because of the Dirac fermion that existed before, that's pulled by the electric field, that now, when you polarize the F electrons, doesn't gap enough. But the prediction, for example, which this prediction wasn't available in the Hartree-Fock studies because we missed it, because they're not very easy to do, is that, for example, in mu equals 0, the KAVC is a Chern number 0 state. But as you increase the displacement field above, I think, 300 electron volts, you go into a Chern state, into a Chern correlated Chern insulator state. So this is kind of a very easy to check prediction. You just increase the electric field and you go into a Chern state. And this is my last slide. So we are trying to get some more heavy fermion mappings. And it turns out that there is a heavy fermion mapping for another model, theoretical model of Hongyao, that this is not yet experimentally realized because of lack of 2D checkerboard, I guess, materials of the right filling. But the 2D checkerboard has a quadratic in the single layer, has a quadratic null touching at the endpoint, and he twists that. And you again get some topology of the same type as here. The topology actually is, as in TBG, the topology actually has an Euler number that's twice as high as here. So it's actually just 2 copies of this topology, but with the same number of bands. But you can still see that the charge becomes localized in some areas. And you can see that the heavy fermion description actually of this model also works, right? I mean, you can't see, but you can trust me that it also works for a large range of parameters. Now, we don't know if the experimental parameters are in this large range, but this is because we don't have an experiment here. But there might be a reason why somehow, when you twist these samples, the charge density localizes in some areas, especially at some magic angles that would make these heavy fermion descriptions more general than just twisted by layer. So with that, I took enough of your time. So I wanted to thank you for your attention.
Okay, we have time for questions. Just let us get the volume sorted out. Okay, questions. Elio has a question.
I have a question about the implications of this heavy fermion model for, let's say, STM experiments. So it seems to me that when temperatures are higher than any symmetry breaking temperatures, but still much lower than U, which is currently the largest scale in the system, it is, I mean, it is disadvantageous to tunnel onto the F electron sites. Right? Is there anything where you would see that in STM data?
So there's certainly many differences in tunneling in very good. So yeah, very good question. So there's certainly many differences in tunneling on the AA sites and on the AB sites, and these are differences both on. So map, when you tunnel, you get something. This is when you tunnel on the AA sites. Where is it? You get something that looks like this. So you get something that looks like this. Okay. Now, and this is a large. This is a very, so you see AA site, and you don't get similar things. Well, you get different things when you tunnel on AB sites. Yeah, but so it's kind of enticing to kind of, you know, interpret these as some Condor resonance approaching the Fermi level. But I don't, you know, I don't have. Well, first of all, I don't have enough. I have almost zero experience in Condor to be able to make comments on this. But experimentally, there are differences between the AA and AB sites, and there's things that are coming in clearly sharp resonances that are coming into to at least the integer filling. So all of these are integer fillings here. The integer filling experiments. So the real answer is I don't know more than that. But I agree with you that at high temperature there should be a signal, and this is a high temperature signal. Like there's no correlated states here, by the way. In this is, I think, 5 Kelvin or something, 10 Kelvin. The correlated states will appear as small mini gaps here, and they appear at lower T. So I think this is actually, yeah, some 5, 10 Kelvin, something large. And you can see this even at much larger temperature. So I agree with you, but there should be differences, and I think there are, but I have no prediction for this in terms of Kondo. But they look like some sort of a resonance coming in, right? So, thanks. Very good.
Any other questions? Let me ask one. So now you've got the kinetic energy, presumably one can start to solve the superconductivity problem. Do you have any thoughts on that?
So yes, so I mean, I have, okay, so I have a, let me just get a more cleaner page. So I have, I'm not sure if thoughts, I have some calculations that actually turned out to be useless. And then I have some conjectures. So the calculation number one that we did is to look at so there were many, there were many predictions, one including ours, of phonon, right? I think those are not likely anymore. So the phonon predictions were using the Bicester-McDonald flat bands. But now, if you take the phonon, if you take the beginning dispersion as the dispersion around the charge insulating state, around the correlated insulator states, right? These are now dispersive. So for example, this is filling 2. So as you go to filling 2.1, where superconductivity appears, you start filling in these guys. And if you take the electron phonon interaction projecting onto these bands here, you find out that it's very small and it's overwhelmed by Coulomb. So the electron phonon doesn't give you superconductivity. Now, as an interesting fact, I mean, not an interesting fact, experimentally it's not interesting. Theoretically, it's interesting. If you can use the heavy fermion formalism to actually obtain the potential VKK prime from a phonon projected into the Bicester-McDonald flat bands, which is not the correct thing to do because these superconductors appear next to the insulator, so you should really be projecting to the excitations of the insulator. But if you project into the Bicester-McDonald flat bands, which is what everybody did who did these predictions of electron phonon superconductivity in TBG, then the heavy fermion description allows you to actually obtain an analytic form for this guy and to see that the superconductivity would be nematic in this case. But this is not the correct thing to do. And if you project into the bands on top of the correlated insulator, you find that the electron phonon interaction is much weaker, about 2 orders of magnitude than the Coulomb. There's no way of getting superconductivity here. Now, the only hope, I would say, well, not the only hope, but the thoughts that we're looking into now is that the F electron has a large Hubbard U on site, but actually off site, it goes down by about an order of magnitude. So because of the localization of the binding state. So if the pairing is off site, then you might have a chance of not competing with the Coulomb. So we're now doing, well, now by we I mean Shida is doing RPA on the heavy fermion model to try to obtain the offsite, conductor channel, if there is one. But I think the phonon one is pretty much now, I would say I don't believe it anymore.
That's very interesting. Thank you very much. Actually, one of the mechanisms that we would like to transmute from heavy fermions is the idea that the Hund's interactions could actually drive local pairing, but we should talk about that later.
Okay, yeah.
Gunnar, yes, where are you, Gunnar?
Yeah, right. Just a quick one. So you mostly talked about filling 0 and -1. So would it be correct to think that the heavy fermion bands become less important, sort of, if you increase the filling, or is it just that you can fill the F electrons correspondingly more, and you still have a flat band near the chemical potential?
Yeah, so very good question. So it's the latter. You just fill in the heavy electrons. So you just, I just put in more. You just at filling. So I just talked about filling 1 and 0 just for lack of time. I can, in the paper we did filling 2 and 3. You just fill in more F electrons. Now the bands change like just in the same way that at filling 1, you move it, it's moved by the chemical potential obtained from the F electrons acting on the C is moved up or down. The bands look a bit different. So for example, at filling 2, you move more. Okay, you move it even more. So the band at filling 2 will look like this, and etc. So so this guy would not be flat anymore. Would become like more like this at filling -2, because you move them down a bit. So you can do the same at filling up to filling -2, and you get a full gap, meaning you can see this, right? You can see this full gap here. Sorry, you can see this full gap. Now, if you do this for filling 3 or -3, you don't get a full gap anymore. You get a gapless dispersion. And that basically tells you that that's the wrong ground state. Alternatively, if you do the neutral excitation, you're going to get negative neutral excitations at filling 3. So this tells you that at filling 3, this parent state that you started with, this type of parent state at filling 3 is the wrong ground state. And I don't have any ideas on what the true ground state is there. But, Piers and Liam have some. So but I do know that this trial state of filling 3 and -3, it's inconsistent. It's self-consistently inconsistent. In other words, you try it, you do the excitation spectrum, and it's the wrong ground state. But at filling 0, 1, and 2, it gives you correlated states that are gapped. So at least it's a consistent, self-consistent ground state. And in the strong coupling, you can prove that these are exact states.
Okay, brilliant. Thank you.
Thank you. Very good.
Two great lectures, Andrei. Thank you so much for sharing all of this with you. We only wish that we could have joined you for dinner and talked afterwards, but maybe in a future year you can come to London.
That'd be fantastic. Thank you.
And look forward to talking to you very soon. Thanks very much.
Thank you so much.
Okay.